Hi everyone, Kevin here. We're back with video number 4 in module 8a. Let's get going. Here are the topics in the module. We are on number 3, reactive oxygen species. Life coexists with oxygen. That might not be surprising, but oxygen is a powerful oxidant. Oxygen is actually a toxic gas, and so we have evolved ways of living with oxygen. The characteristics of oxygen itself also allow us to live in oxygen when thermodynamically we should combust. We should burn up just like a campfire on the beach, because thermodynamically reactions of molecules in our body with oxygen are favorable. The delta G is less than 0, as you remember from back in chemistry. That makes it thermodynamically favorable, and we would normally combust in oxygen. But there are two reasons we don't, or two reasons we can live in oxygen. One is that there's a kinetic barrier to reaction of oxygen with molecules in our body, and we're going to talk in detail in this video about what that kinetic barrier is all about. Thermodynamically, we should combust. Kinetically, reactions of molecules in our body with oxygen are very, very slow, and that's the good news. The other reason we can live with oxygen is that we have evolved antioxidant defenses, and we're going to talk about those more in the next video. So, as I said, O2 is a strong oxidant. When we respire oxygen, this is the reaction that happens. So O2 molecules pick up 4 electrons and 4 protons, and the O2 bond, the oxygen-oxygen bond, is actually broken, and 2 molecules of water are formed. In the next video, we'll talk more about the addition of electrons one at a time to oxygen and what that means for reactive oxygen species and oxidative stress. But this is the overall reaction. The main point here is that oxygen is a very strong oxidant. So we talked about reduction potentials in the last video. The reduction potential for the reduction of oxygen to water per electron is 0.8 volts. That is very, very high. In other words, oxygen is a very strong oxidizer. Its tendency to get reduced is very strong, positive 0.8, and that is on a scale with H2 gas, the formation of H2 gas at 0 on the scale. I'll show you that in a sec. In fact, I'll show you that right now. These are some biological reduction potentials, and they're written on this in this little table here. So we go from the oxidized to the reduced form. So if we reduce acetate to pyruvate, 2 molecules, you're probably familiar with acetate. You'll be familiar with pyruvate when you take biochemistry. When we reduce acetate to pyruvate, the reduction potential is a negative 0.7. And again, this is on the scale with, I'm circling now, hydrogen, the 2 protons becoming hydrogen gas, picking up electrons and becoming hydrogen gas. That is set at 0 on our scale of reduction potentials. So on that scale, acetate to pyruvate is very low. But look at the high side of this table, and you'll see oxygen. It's a little cut off here by the video, but you'll see the video of me, that is, but you'll see that oxygen is 0.8 volts. It is, in most biological systems, the strongest oxidant out there. So oxygen is going to attract electrons to it from all these other biological species. The only time that oxygen has a stronger oxidant in the system is when you're dealing with photosynthesis, because the Z scheme in photosynthesis is set up to split water and form oxygen. So in that case, what's shown here is the reduction of oxygen to make water In photosynthesis, this goes in the actually in the opposite direction. We split water and make oxygen. That means in photosynthesis there has to be an oxidant stronger than the O2 H2O couple, and there is in the Z scheme. And we won't talk about photosynthesis in this class, but when you do talk about photosynthesis in biochemistry, you'll see that there is a stronger oxidant than oxygen. But in general, other than photosynthesis in biological systems, oxygen is the strongest reductant out there. Here's the problem. The high reduction potential of dioxygen, and we often just say oxygen, but formally we should say dioxygen, because when we're talking about oxygen gas, we're talking about O2. The high reduction potential of dioxygen has its drawbacks. Dioxygen is among the strongest oxidizing agents in biological systems, and therefore has the thermodynamic potential to oxidize most organic molecules. That's what I just said. Here's the good news. Luckily, dioxygen has a built-in kinetic barrier to oxidation in the form of two unpaired parallel spin electrons. To react with dioxygen, incoming electrons, say electrons that would come from a molecule in our body, must have parallel spins of their own or be added one at a time. Now, most of our molecules don't have parallel spins. Most of the electrons in our molecules are paired with an electron of opposite spins, opposite spin. Therefore, they won't. Our molecules will not readily react with oxygen. So when oxygen reacts, it usually reacts one electron at a time. All right, and this, you can finish this quote. Since most organic molecules contain only paired electrons, spontaneous reactions with dioxygen are slow. And that's the key. Thermodynamically, we should combust in air, but luckily, we do so very, very slowly because of this kinetic barrier. So, molecules that do readily react with dioxygen, such as transition metals and free radicals, contain unpaired electrons. And we're going to look at that at the very end of this video. But that is key, and that's key to oxidation in wine, because typically oxidation starts by the reaction of oxygen with transition metals like iron and copper. Let's look at the electrons and look at those unpaired parallel spin electrons. First, let's look at oxygen. So if these are the atomic orbitals of the atom oxygen, ignoring the molecule for now. If we were adding electrons to these, we know that oxygen has an atomic number of 8, so there are 8 electrons. And if we add them in, we get 2 in the 1s orbital, 2 and 2s. Then we add them one at a time to the 2p orbitals, and we follow Hund's rule, which says that if we have degenerate orbitals, which mean multiple orbitals with the same energy level, that we're going to add the electrons to those orbitals such that we have the maximum number of unpaired electrons. So that means electrons 5, 6, and 7 in oxygen go into individual 2p orbitals. The 8th electron then we would add to one of those 2p orbitals, and so we would have one orbital with a pair of electrons with opposite spins, but we'd have 2 orbitals with electrons that are unpaired. All right, so this is oxygen itself. That prior slide was the atom oxygen. Here, let's look at how 2 atoms, oxygen atoms, combine to make O2. So the 2 oxygen atoms are shown on the left and the right in this picture. And if we added electrons, just like we did in the last slide, to each of the atomic orbitals, it would look like that. Now, when these combine to form molecular orbitals, we know that 1s orbitals would combine to form 2 sigma 1s orbitals. One of those sigma 1s orbitals would be bonding, that's the lowest energy, and the one with the asterisk or the star is the anti-bonding orbital. 2s then also forms sigma similarly forms sigma bonding orbitals, sigma orbitals, one bonding and one anti-bonding. And then the two p orbitals combine to form both sigma and pi orbitals, depending on how geometrically the orbitals are arranged. The ones that pair end-to-end form the sigma bonds, and the other form the pi orbitals. And again, we've got bonding and anti-bonding. So the bonding sigma 2p is lower than the anti-bonding 2p in energy, and the pi 2p is lower than the anti-bonding pi 2p. And of course, these orbitals are arranged, I didn't draw it on here, but this in increasing energy, and I'm not sure I can write on the side. It's pretty messy, but you get the idea. Increasing levels of energy. All right, so let's fill in those O2 orbitals. And if we take the 16 electrons in O2 and we fill orbitals in increasing levels of energy, that's what we get. At the top are the two unpaired parallel spin electrons in a pi star 2p orbital. All right, or orbitals. We've got two parallel spin unpaired electrons. If you count the electrons, both bonding and anti-bonding, on that prior slide, you'll see that we have 10 bonding and 6 anti-bonding. That means we have a net of 4 bonding orbitals, the 10 minus the 6. If we divide that by the 2 atoms that are bound by those 4 orbitals, we get a bond order of 2. Or in other words, oxygen has a double bond. And that's shown at the top here in this picture, where we show the 16 electrons. Well, we don't. We show the valence electrons in this picture, but we show the lone pairs in the outer orbitals and the bonding the 4 bonding electrons between the oxygen molecules. So we have a double bond. We'll come back to this table as we add electrons to oxygen to form other reactive oxygen species, and we'll look at the bonding and anti-bonding orbitals and how the bonds change as we go along. We'll do that in the next video. So once again, it's those parallel spin, unpaired parallel spin electrons that are the kinetic barrier to reacting to oxygen reacting with organic molecules. And this reaction scheme at the bottom here shows that. So we've got ground state oxygen here with the 2 unpaired parallel spin electrons. The 3 in front of oxygen means it's triplet oxygen, which indicates the ground state with the 2 unpaired electrons. It's the lowest energy configuration. Don't worry about what triplet means right now. We'll talk about it later. Take it just for now as ground state. The X in this picture is any organic molecule. And in organic molecules, normally, all the electrons are paired with an electron of opposite spin. And that's what's indicated by the 2 arrows with opposite directions here. So when that organic molecule reacts, when it reacts with oxygen, it is going to form XO, or this oxidized version of X, and it's going to need to have electrons that are paired. Well, as that paragraph showed you a few slides back, or as it described a few slides back, unpaired parallel spin electrons are not going to react with paired electrons with opposite spins. It's just not going to happen. So this reaction is very, very slow, and that's the kinetic barrier. So as we said, oxygen often reacts 1 electron at a time. So oxygen reacts with free radicals. Free radicals are molecules with unpaired electrons. We'll talk more about free radicals, and they're going to be important in wine in oxidation. Because of those parallel spin electrons, oxygen picks up electrons 1 at a time, and it'll do so from free radicals that have an unpaired electron. It'll also do so from metal ions. So things like iron. Iron 2+ can get oxidized to iron 3+ by donating an electron to oxygen. And we'll see how that happens in wine. Copper plus, likewise in wine, will donate an electron. In biological systems, there are other molecules that are built to stabilize one electron. Coenzyme Q is a carrier of one electron at a time in the electron transport chain. If you've had biochemistry, you will have seen this. If you are taking it now, you'll see it soon. But this is a carrier of one electron at a time. Its molecular structure allows it to be a fairly stable free radical. Riboflavin, likewise, can carry one electron at a time and be a fairly stable free radical. Usually free radicals are very reactive, but some more so than others. And we're going to talk about that because that's important to the antioxidant properties of the phenolic compounds in a wine. Remember, we talked a little bit about phenolic compounds, and we said that they're antioxidants. And it's because they can stabilize an unpaired electron. They can become free radicals, but fairly stable free radicals. We'll talk more about that. But when it comes to reacting with oxygen, free radicals and metal ions are where the action is. That's it for this video in Module 8A. We'll pick up in Video 5 talking more about reactive oxygen species, and I'll see you then.